नमस्ते बच्चों, हमेशा खुश रहो बच्चों। Myself Om Prakash, Faculty of Department of Mathematics under Faculty of Education and Methodology, Jyoti Vidyapeeth Women's University, Jaipur. Today I taught you group theory. The subject group theory is taught in BSc, BA, BCA, 6th semester student. These are the lesson planning. These are the steps for planning valuation. These are the components of valuation plan. All of these are already taught in your first lecture. Now, in group theory is a subject of mathematics under science stream, which are taught in BSc with BCF 6th semester student. In your last class, I will see some theorems on subgroup of a group. I will extend some more theorem on subgroup of a group. Here, this theorem is the necessary insufficient part to be a subgroup. Here, the statement is prove that the necessary insufficient condition for a non-empty subset H of a group G. Prove that the necessary and sufficient condition for a non-empty subset H of a group G to be a group are that of A belongs to H, B belongs to H implies that A star B belongs to H, and A belongs to H implies that A inverse belongs to H. A belongs to H implies that A inverse belongs to H. That means the first property shows the closure axiom and the second property shows the existence of inverse. If the closure axiom and existence of inverse holds a good in a subset H of a group G, then the subset H is said to be subgroup of a group G. Or we can say H is also a group. Now for this, we first prove the necessary part. The necessary part says that let H be a subgroup of G. Let H be subgroup of G. Then we have to prove that H is also a satisfies equation 1 and 2. Then by definition of subgroup of a group G, H satisfies closure axiom, associativity, existence of identity, element and existence of. Therefore 1 and 3 satisfied by closure axioms and existence of inverse respectively. That means nothing has to prove for the necessary part. Insufficient part, let us consider, or we can say conversely, let us consider the given condition 1 and 2 holds good in H. 1 and 2 holds good in H. Then we have to prove that H is a subgroup of a group G. For this, we have to prove that H is also a group. For this, it satisfies the axioms of a group. The first axiom says that let A, that means closure axiom, let A belongs to H and B belongs to H implies that A star B belongs to H, which are already given in equation 1. Next one is the associativity. Again, let A, B, C belongs to H implies that A, B, C belong to G, since H is a subset of G, and this implies that A star B star C equals to A star B star C for all A, B, C belongs to H, which are the subset of G. See, and this is why, because G is a group, and in any group, associativity holds good. Therefore, associativity holds in H also. Next one is the existence of identity element. Here, let A belongs to H. This implies that A inverse belongs to H. That was given in equation 2. Then A star A inverse belongs to H because closure axiom holds in H. But we know that A star A inverse equals to E, which belongs to H. That this is the property of identity element. Therefore, we can say that existence of identity element in H. Next one is the existence of inverse, which are already given. Since the inverse of each element of H is in H, given by equation 2. Hence, we can say that H satisfies all the conditions of group. This implies H is a group, but H is subset of G, which is a group also. Then, by definition of subgroup, H is a subgroup of a group G. Then, by definition, H is a subgroup of a group G. This is hence the theorem. Now, we are going to prove the second theorem, which are also the necessary sufficient part. In the previous theorem, I will see the two conditions. First one is the closure action, and second one is the inverse. This theorem is the combination of these two conditions. That means if A and B belongs to H, this says that A B inverse belongs to H. B inverse shows if the inverse exists, B belongs to H, therefore B inverse belongs to H. And the A and B inverse are element of H, therefore A star B inverse belongs to H. If the previous theorem is holds, then this term holds by default. Now we have to prove these things. For this, we have the statement of the theorem is prove that the necessary and sufficient condition for a non-empty subset H of a group G is subgroup of G is that A, comma B belongs to H implies that A star B inverse belongs to H. Again, we take the necessary part. Let H be a subgroup of a group G. If F be a subgroup of a group G, then this implies that H itself a group. H is itself a group. Therefore, A, comma B belongs to H implies that A, comma B inverse belongs to H. Existence of inverse in H. This implies that A star B inverse belongs to H. Closure axiom in H. Hence the theorem. That is the necessary part. Now, next I will move to the sufficient part of this theorem. The sufficient part of this theorem says that conversely, let the given condition holds in H. That means A, comma B belongs to H implies that A star B inverse belongs to H. Now, for closure action, let B inverse equals to D. Then A star D belongs to H for all AD belongs to H. This implies that closure axiom holds in H. This implies that closure axiom holds in H. Now, next one is the associativity. Let A, comma B, comma C belongs to H. This implies that A, B, C belongs to H. Since H is a subset of G and G is a group, therefore we can say A star B star C equals to A star B star C. All of this belongs to H subset of G. This is why, since G is a group. Since G is a group, that means we have to closure action and associativity action. Next one is the existence of identity element. The existence of identity element. Let A belongs to H. B an element. If H is not equal to 5, then A, comma A belongs to H. This implies that A star A inverse belongs to H, and A star A, which are given. This implies that A star is equals to E, which belongs to H. Therefore, identity element exists in H. Next one is the existence of inverse. This is the last condition for a subgroup for a group to be for a set to be group. From above, A, comma A belongs to H. This implies that A, comma star A inverse belongs to H. This implies that E belongs to H. Then E star A inverse belongs to H. Implies that A inverse belongs to H. This implies that H has inverse of each element of H. Each element of H. Hence, H forms a group and therefore a subgroup of G. Therefore, a subgroup of G. Hence, this proves the theorem. This proves the theorem. This session is powered by the digital version 2.0 JAYOTI Vidyapeeth University, Jaipur, and I hope all of you are satisfied with crystal session. If you have any queries, please mention in the comment box. I will try to resolve it. Thank you for watching my this lecture video. Thank you.